Thank you for reminding me to put my mic on, Jens. Yeah, thank you all so much for coming to learn about the work that I've been doing over the last 5 years, and thank you, Jens, so much for the kind introduction. So part 2 of 6, thank you for those of you who are coming for the second talk today. Today we're going to be talking on a slightly different subject, and that's that of methane oxidation to methanol. It is estimated that over 2,000 trillion cubic feet of natural gas are lying in the Earth's crust. Natural gas can be used as a fuel to power our buses, to heat our homes, or to cook. And it can also be used as a chemical feedstock to make chemicals such as hydrogen gas. However, natural gas, as the name implies, has a very low boiling point and is a gas at standard temperature and pressure, which makes it very expensive and difficult to transport. The way that we get natural gas to our homes and businesses in the United States is through a vast array of natural gas pipelines, like the one shown here. But of course, these pipelines can't exist everywhere. In particular, when natural gas is pulled up alongside of crude oil at remote oil drilling locations, and there isn't a neighboring pipeline to put that gas into, it's simply burned or combusted to form CO2. This problem is large enough that we can actually see it on satellite imaging of the United States at night. So here you see all of the large metropolitan areas, as you might expect, are lit up. And we also have this somewhat suspicious blob of light over here in North Dakota, where there is no large metropolitan area. And this, in fact, is the flaring or burning of natural gas. This flaring process around the world accounts for almost 1% of global CO2 emissions. And this is, of course, with no associated energy gains. So burning off those fossil fuels, not getting anything in return. What can we do about it? Well, we'd like to find a process that could be used at the wellhead, so in a delocalized manner, where we'd be able to transform methane, the primary component of natural gas, into something that was more transportable or more valuable, or both. And that's where this reaction methane to methanol comes in. So taking a single oxygen atom and inserting it into one of methane's CH bonds, methanol is a nice product to think about for this reaction because it retains 64% of methane's chemical energy, which means that it can still be used as a fuel, while at the same time now having a 400 times higher volumetric energy density because it's a liquid at standard temperature and pressure. This reaction has been termed one of the holy grails of chemistry, which should be indicative to you not just of the value of such a reaction, but also of its elusiveness. So why is it so difficult to find a direct process that can turn methane into methanol? This process is actually done currently in an indirect two-step manner, whereby first methane and water are converted to a syngas mixture of carbon monoxide and hydrogen, and that's uphill in energy by 2 electron volts. And then that syngas mixture is converted to methanol. But this first step, being so uphill in energy, means that we have to go to high temperatures and pressures to get this to run, and that means that we have to do it in a centralized production facility. We can't have it delocalized at the wellhead. So going back to this question of why it has been so difficult to find a direct methane to methanol process, there's 2 main reasons that are often cited in the literature. The first is activity. So the methane molecule is sort of an energy stronghold. It's very shielded from chemical attack, and that has a lot to do with its very weakly polarized bonds. So carbon and hydrogen have very similar electronegativities. And then what small dipoles do exist in those bonds are basically made into nothing when you go at a distance due to the tetrahedral symmetry that exists in methane. So it's essentially invisible to chemical attack. The second reason that has been cited is selectivity. So imagine that you are able to activate methane. Methane has CH bonds that are quite strong. They release 4.6 electron volts of energy upon breaking. Some of these oxidized products, I've shown methanol here, and also formaldehyde is another option. Their CH bonds are also strong, but weaker than those in methane. So if you go to conditions where you're going to be able to activate the CH bonds of methane, you can bet that you'll probably also be able to activate these products, and then you'll cascade down the thermodynamic potential energy surface to CO2. And now you're doing no better than burning the natural gas. So to get into these two problems, we have to do a little bit of background. And the first thing that I'll talk about is kinetics. So how do we determine whether a catalyst is active and selective? So here I'm showing a toy reaction, A and B going to C and D. And there's two quantities of interest here that we need to think about. The first is the thermodynamic driving force, or delta G. So how much more stable, in this case, I've drawn an exergonic reaction, how much more stable are the products than the reactants? And the other quantity is the free energy of activation, GA. And this effectively, this is the barrier that is required to get from products to reactants. And this tells you about how much time it will take for your system to reach thermodynamic equilibrium. We can write the rate of going from our reactants A to B to our products as the partial pressures or concentrations of A and B times the molecular rate constant in the forward direction minus the partial pressures of the products times the molecular rate constant in the reverse direction. These molecular rate constants are written here, and we can see that they're a function of temperatures, constants, and of course these two quantities, the free energy of activation and the thermodynamic driving force. So how we find these quantities, GA and delta G, in practice can be done in a multitude of ways. One of the ways to do this is to use simulation and computational methods. So we use in our group something called density functional theory, where we are solving the many-body Schrodinger equation, shown here, to find the electronic wave functions. So the first term here is related to the kinetic energy of the electrons. The next term is related to the electron-electron interactions. And the final term is related to the all of the electrons interacting with the collection of nuclei in the system. Some very smart people a long time ago realized that there's a lot of extra information in wave functions that you don't really need to fully describe the electronic ground state of a system. They found that actually all you need is the electron density in the ground state, which we call NR. And so now we can sort of rewrite this many-body Schrodinger equation in the form of an energy functional, F of N of R. And now these terms are analogous to the ones above. We've rewritten them, also leaving out the terms that we don't really know how to solve exactly. So the first term here, which we do know how to solve for exactly, gets most of the kinetic energy of the system, but not quite all of it. This is the kinetic energy of a system of uncharged particles or uncorrelated particles with the same density as our system of electrons. The second term is the uncorrelated Coulomb energy. The third term is just the electron interacting with the nuclear collection again. And the final term, the exchange correlation functional, is really just this fudge factor where we've kind of grouped in all of these little terms that we don't really know how to handle. There's many different estimations for what this exchange correlation functional is, and that's sort of where these different flavors of DFT come in. So some of the different ones, lots of acronyms over here, those are all different exchange correlation functionals. The important thing to take away from this plot is that we are going to be using two called RPBE and Beef van der Waals in this work, which have been shown when calculated against an experimental chemisorption database to have mean absolute errors on the order of 20 kilojoules per mole, or about 0.2 EVs. So that should give you an idea of the resolution that DFT is capable of. So density functional theory gives us the ability to find the energy and forces at any point on the potential energy surface of our system, shown here. Using DFT then, we can relatively easily, using a variety of minimization techniques, gradient descent or Newton's method, take your pick, find our way into a local minimum of energy and call that the ground state energy of the system. The local ground state energy. Transition states, however, can also be isolated using DFT, but it's much more computationally expensive, much harder to do so. So in practice, we use something called the nudged elastic band method, or NEB method, where we linearly interpolate between our ground state, between our initial state and our final state, some number of images. We attach a fictitious spring force between these images so that in the relaxation they don't collapse into the local minima nearby. And then we relax the system. And this is showing here in black. Here's the original linear interpolation between a initial state and a final state. After 243 iterations of this process, we relax to the red line shown here, which is showing the pathway, the lowest energy pathway between these two species. And here you can see that from that initial reaction to the final lowest energy pathway, we drop down by about 0.5 electron volts. So we would really like to avoid these expensive calculations in practice. If we could get all of the information that we need just from calculating electronic ground states, then we would be able to do catalyst screening much more quickly. But of course, kinetics depends on barriers. It depends on these energy saddle points. And that's where transition state scaling relationships come in. So luckily, it has been observed in the past. People have noticed correlations between these transition state energies and the thermodynamic driving forces, or the ground state energies of a reaction. So here I'm just showing the driving force of several reactions of one reaction on several catalysts and the activation energy. And you can see that as you increase the driving force from gold to blue, you also decrease the barrier to get to the product. This can be more easily visualized if we plot the delta E versus the activation energy. And we see that we have a relatively linear scaling relationship, or linear correlation between these data points. So this is really nice because it means that we can estimate our activation energy without doing these expensive NEB calculations as a function of two local energy ground states. These transition state scaling relationships have found many uses and been very useful throughout the literature. But there are some things that you have to keep in mind when you're using most of them. So namely, if you're trying to compare a reaction on one catalyst morphology to the same reaction on a different catalyst morphology. So here, for example, we're looking at terraces versus step sites on a metal surface. There's something called the geometric effect that comes into play. And that will often make it so that you have two different BEP scaling lines for each of these different surfaces. So if you want to calculate the transition state of CO dissociation on a step, and you only have energies for CO dissociation on terraces, then you have to be careful. Okay, so done with the background. Going back now to the original questions at hand. How can we understand methane activity and create or screen for catalysts that have good methane activity? So the first thing to note with regard to this question is that in heterogeneous catalysis, generally there have been two different mechanistic pathways that are observed for methane activation. One of these is the surface stabilized activation pathway shown here on the left. And here you can see that the methyl group is interacting with the catalyst surface during the transition state. You can also see that the CH3 group remains relatively sp3 hybridized in the transition state. In the radical-like pathway, however, you can see now that the CH3 group is not really interacting with the surface at all. Instead, it's starting to go into sp2 hybridization, or becoming more radical-like. So because radical-like activation is very important for a lot of single atom catalysts that have been very successful for methane to methanol in the past, such as zeolites, we're going to focus in on this activation pathway. So this work was done in collaboration with Ambarish Kulkarni, a former postdoc in our group who's now a professor at UC Davis. And what we did was to look at methane activation in the radical pathway on a variety of different catalyst surfaces shown here. We define a parameter that we'll call the hydrogen abstraction energy, or EH, which is just the energy of the hydrogenated active site minus the energy of the clean active site, or the unhydrogenated active site. And what we find is that the transition state energy across catalyst morphologies scales as a function of this hydrogen abstraction energy. with a mean absolute error of only 0.1 electron volts, which is about half of what I showed earlier, the DFT resolution when compared to chemoabsorption experiments. So that says to us that this scaling relationship can be used confidently within the resolution of DFT without the need to use any calculations. We can also see that the scaling transcends catalyst morphology. So we seem not to have these geometric effects that could be so troublesome for DET. When we recognized that methane activation scaled as a function of the hydrogen abstraction energy, we also thought about the fact that this might describe other molecules where a CH bond is being broken. Because if you think about it, nothing in that descriptor had to do with the CH3 group on the other end. So we switched out the CH3 group and we started looking at things like ethane and methanol, and we asked if we would find similar trends. And the answer is yes. Now we see that for ethane and methanol, we get the same slope of the scaling relationship for transition state energy as a function of hydrogen abstraction, except the intercept of the scaling has been shifted. How has the intercept been shifted exactly? Well, it turns out that it's shifted just based on the CH bond strength of the reactant. So now this is looking at a single catalyst active site and varying the reactant that's being activated. So 3 of these points are methane, ethane, and methanol. And we see that now the transition state scales linearly as a function of the CH bond strength. This means that we can identify a cohesive scaling relationship for many reactants and many catalyst surfaces, where the first term describes the catalyst that we're looking at, the second term describes the reactant that we're looking at. We can use this relationship to make a parity plot of our model's predictions versus the density functional theory calculated transition states, and we see that we do quite well. A final thing that we can do with the scaling that we found, again, we're interested in rates, so let's think about rates of activation of methane. If we want to do that, then we need to think about how likely it is for the active site to be present on the catalyst in the first place. So that's what this theta motif term is. This is the coverage of active site that you're expected to have at your conditions. And the second term is the molecular rate constant for methane activation. And of course, we know that the free energy of activation now is related to EH. We've assumed a couple of things in this model. The first is that you have active site equilibration with oxygen gas at 450 degrees Celsius, so a high temperature. And this will describe the theta motif term. And then the second assumption is that we have rate determining methane activation at a lower temperature, 150 degrees C. And this is really just to mimic the experimental methods for zeolite chemistry to better compare our results. So with this equation then, we can make a rate volcano where we now have the formation energy of the active site on the x-axis and the hydrogen abstraction energy of that site on the y-axis. And the colors are going from high rates of activation to low rates of activation. Something interesting that pops out of this plot is that for a given catalyst morphology, so here we're looking in purple at mordenite and 303, we see that copper exchange zeolites tend to be the most active. And this is reproduced for several of the other morphologies, including mordenite copper O copper, as well as chabazite copper O. And this is interesting because it has been well known experimentally that copper exchange zeolites tend to be the best performing, and there has been a lot of literature published on these. So it suggests that they are some of the most active cation exchange zeolites. So qualitatively, at least, the model seems to reproduce these results. Okay, so moving on to selectivity. We've explored activity a little bit. And now let's consider the selectivity question. So I just showed this volcano, and let's say now that we've done a catalyst screening, and we've identified some materials, some catalysts that fall in this active regime, maybe in where the white circle is. How then do we know? So these catalysts, we believe, will be able to activate methane, but how do we know that once activated, that methane will go on to form methanol, the desired product? To answer this question, I worked with Dr. Arvind Kakekani, who is a former postdoc in our group, And we devised a simple 3-step model system. So in this model system, we just have methane going to methanol with some rate constant K1, and methanol going to CO2 with some rate constant K2. We assume we only have rates in the forward reaction, no reverse rates, as is typically the case in the very thermodynamically downhill oxidation reactions of hydrocarbons. We can solve the differential equations that come out of this for the partial pressures or concentrations of these species as a function of time, and we can plot them with some parameters here. So we can see that at the beginning, we have nothing but methane, but that methane concentration quickly decays. And eventually, as time goes on, we have only CO2, our most favorable product. At some intermediate time, we have our maximum concentration of the product we're interested in, or methanol. So that's really kind of the area that we're interested in. But we need to sort of rewrite all of this in terms of selectivity and conversion, as these are the sort of experimentally important quantities for this reaction. This is a plot from a recent review paper showing the methanol selectivity on the y-axis as a function of methane conversion. And what you can see is that there exists some correlation between these two quantities. In particular, it doesn't seem possible to get high methanol selectivities while also maintaining high methane conversion. This is underscored by the fact that the x-axis here goes from 0 to 12% methane conversion. So switching all of our, or we can define the conversion of methane as the amount of methane that has been consumed divided by the amount of methane that there was to begin with, and the selectivity towards methanol as the partial pressure of methanol divided by the amount of methane that has been consumed. Combining these two equations and doing some algebraic manipulations, we can arrive at an expression for selectivity as a function of conversion of methane and this ratio of the two rate constants, K2 over K1. We can now explore what this expression looks like as we vary the quantities in it, the parameters in it. So if we hold delta GA, which is another way of saying K2 over K1, if we hold delta GA constant and we vary temperature, you can see that from going from a low temperature to a high temperature is favorable for us. If you're looking at 300 Kelvin, you can only maintain high selectivities at log methane conversions of 10 to the minus 7 or 8. But if you're at 700 Kelvin, now that conversion jumps up to 10 to the minus 2 or so. We also see that if we hold temperature constant and we vary this difference in the rate constants, we would like to have a delta GA that is very small or even negative. And what this corresponds to is effectively saying that we want methanol to be more difficult to activate than methane. So let's quantify this K2 over K1 term, since that's really the only unknown in our equation. So assuming that CH cleavage barriers are rate determining, which is often the case in these sorts of chemistries, we can define this delta GA as just the difference between the methane activation barrier, or the methane CH bond cleavage barrier, and the methanol CH bond cleavage barrier. And so now we can write K2 over K1 is just the exponential of the difference in energy between these two barriers, which we call delta GA. So now we're really interested in quantifying what delta GA is then. Delta GA is a function of temperature, and it includes all of these terms shown here in order to get thermodynamic delta GA. So the first one, the difference in electronic energy, this is what we get out of density functional theory calculations. So here I'm showing density functional theory calculations where I've plotted the activation energy, electronic energy of methanol on the x-axis versus that of methane on the y-axis. And what we can see, this should be a little concerning to you, is that there is a very good correlation there. And this was sort of hinted by the previous work that I showed as well. We can show this a different way by subtracting the methanol activation energy from the methane activation energy and plotting a histogram of that quantity. And what we see is that it has a very narrow distribution with a sigma of about 0.08 electron volts, centered around a mean of 0.55 EVs. So what this says is that on average, methane is 0.55 EVs more difficult to activate than methanol, which is the opposite of what we would like. To get all of these other terms, we can use density functional theory and some approximations to get those. But the important thing is that what we find is that the delta GA as a function of temperature is approximately a linear function of temperature given by this expression here. We can plot the delta GA just for example at a finite temperature. So here we've shown it at 300 Kelvin. And you can see that again, it's approximately normally distributed with a very tight standard deviation and a mean at 300 Kelvin of 0.41 electron volts. Okay, so now that we've quantified K2 over K1 using density functional theory, we can plug it back into our selectivity expression and see what we get. And that's shown over here on the right. We're now plotting this at a temperature of 550 Kelvin. In black, I'm showing this expression with the K2 over K1 from DFT. And all of the gray is showing the plus or minus 1 sigma, one standard deviation of the scaling. Now what we can do is plot experimental data on this curve. And so this is data out of the Panov group where they were looking at a certain zeolite for continuous methane oxidation. And we see that it fits the ab initio model quite well, not only in the location of the data points, but also in the general shape that we see. So encouraged by this, we moved to exploring more experimental data and got what we could find out of the experimental literature, and that is going to be shown here. So in the experimental literature, we found a wide variety of different reaction conditions, reaction temperatures, catalysts. We went from homogeneous to heterogeneous catalysis, aqueous conditions, and gas phase conditions. And what we find in general, and the reason that we have so many plots here is because this is a function of temperature as well as conversion. So each plot is showing a certain temperature plus or minus the data points within 25 Kelvin of that temperature. What we can see in general is that most of the experimental data seems to fit these curves quite nicely, falling within the 1 sigma standard deviation of these curves. And we can also see that the aqueous data far seems to outperform the gas phase data in the sense of selectivity conversion limit, Namely, the lowest temperature gas phase data that we could find in the experimental literature was at 475 Kelvin, where we had conversions on the order of 10 to the minus 6. And that's versus the aqueous data, which of course occurs at much lower temperatures. We can visualize this data in a couple of other ways. The first is to assume that the model describes each data point and then fit an effective delta EA experimental to each experiment. And then we can back out sort of a histogram of these quantities. And this is really just to remove the temperature dependence. So here I'm now plotting that theory histogram that I showed originally in gray, but now with the experimental histogram from assuming the model fits to all of these data points. And what we can see is that the two histograms are very similar. They have means that are only 0.04 EVs apart from each other and very similar standard deviations. The second way that we can now use these effective delta EAs from experiment is to extrapolate all of the data to identical conditions or identical temperatures. And so now I'm showing all of the data having been extrapolated to a temperature of 700 Kelvin. And again, you can see that the data seems to mostly fall within the 1 sigma standard deviation. We do have some outliers here on the unfavorable side, but this is not expected because we expect our selectivity conversion expression to really give a limit to the selectivity. Okay, so from this, we propose a couple of design strategies for circumventing or for living with really this selectivity conversion limit that we've identified. The first is that of a methanol collector. So Here we have our delta GA, it's fixed. We can't do anything about that. There's a difference in the methane and methanol activation energies that seems to be unchangeable. But we can affect the initial state. So here, you can imagine having a material that binds methanol very strongly and pulls the initial state of methanol down into a thermodynamic well, but that leaves methane unaffected. Now your delta GA drops by this methanol absorption energy, by this difference in energy here. So a way that you might consider setting up a system like this is to have maybe a two-phase experimental setup where you have one component that is your active phase and one component that is your collector phase. So the active phase needs to be activated by oxygen, maybe by using N2O. Then we're going to flow methane through then a methane will come along and that active oxygen will attack it and form methanol. If we didn't have a collector, this methanol could find another oxygen that would attack it much more quickly than methane because it has weaker CH bonds. But instead, we have a collector material in the system. And now the methanol is going to get pulled onto the collector surface and down into this thermodynamic well. Once we've run this reaction a sufficient amount and filled up our collector surface, then we can stop the reaction and collect the methanol. So what are the properties of a good collector? Well, we want it to strongly bind methanol. We discussed that. It also needs to have been treated to remove all water and OH. Turns out these collectors like methanol, and similarly, they really like water and OH, but this can be achieved with drying. We also need it not to activate methane and not to activate oxygen, so that it's a spectator in all ways except for interacting with methanol. With these qualities in mind, we've actually identified some candidates that follow all of these traits, and you can plot these candidates now as a function of both temperature and of the collector's binding energy. So now I'm showing selectivity in red is good and blue is bad. And we can see that for our best collector, aluminum oxide, we can maintain near 100% selectivity up to about 600 Kelvin or so. And that's up until the collector gets filled up. So the way to think about this really is that the collector is sort of acting analogously to a heterogeneous protecting group that will protect the methanol until it's ready to be collected. Okay, the second design strategy, aqueous reaction conditions. So we touched on a little bit, noticing that these seem to all outperform the gas phase data. But let's dig a little into why exactly that is. Well, it turns out the picture we believe to be quite similar to the collector idea, except now in this case, water is actually acting as our collector for us. So this is because methanol has a solvation-free energy that's downhill in 0.2 electron volts at 300 Kelvin, whereas methane, of course, doesn't. It's actually unstable to solvate methane. So we get a little bit of a boost here, which corresponds to dropping our delta GA by up to this solvation amount, up to 0.2 electron volts. It doesn't sound like much, but if you plug that into the model, in dark blue, I'm showing the original delta GA, and in cyan, I'm now showing the solvation energy corrected delta GA that's been dropped by 0.2 electron volts. We get a big shift. And you can see that the experimental data, plotted again here, seems to really nicely follow this solvation corrected selectivity conversion limit. Whereas it all falls pretty far away from the dark blue. So we think that liquid water can act as a collector too, and we think that this is why much of the high selectivity, high conversion data in the experimental literature comes from aqueous phase reactions. And the third strategy that I'll discuss is diffusion limited systems. So here the picture is a little bit different. We have our delta GA that stays the same, but now let's say that before methane and methanol can get to the surface, they have to diffuse, and they have to cross through some diffusion barrier to get there. As we increase this diffusion barrier, as we increase it up to the methane activation energy level, the delta GA will approach 0, and that's because now the rate determining step for methanol oxidation is changing from CH bond cleavage to the diffusion barrier. whereas for methane, it's remaining the same. You could continue increasing the diffusion barrier above the methane activation barrier, but then you just slow your rates and you don't get any added benefit in selectivity. We think that this is very analogous to what's going on in a particular enzyme that has been found to be very successful for this process of methane monooxygenase. So methane monooxygenase's active site is shown here on the right. So that's the guy that will activate methane and methanol. But its larger structure is shown over here on the left. And that's maybe what is controlling diffusion. So it's interesting, in the experimental literature, much of the zeolite work has been inspired by this active site, having oxygen networks with iron active sites and copper active sites. But we think that there's a chance that these studies are missing out on the diffusion limitations that are also offered by this enzyme in nature. A work that was done in 2002 studying the kinetic isotopes effects of several reactants with methane monooxygenase quote this paper by saying, on the basis of the magnitude of the absolute rate constants, we can conclude that for these hydrocarbons, the activation energies for the two processes, CH cleavage and substrate diffusion, are fortuitously similar. So this is now showing our model just with varying the free energy of activation, going from 0.4 as it is at 300 Kelvin up to 0, which we would expect the limit to be. We can populate this with experimental data for methane monooxygenase. In green is the natural selectivity of this enzyme, natural selectivity and conversion, where it prefers to sit. And then in red are experiments where it was pushed to higher conversions. And we can see indeed that the selectivity of methane monooxygenase drops off as it is pushed to higher conversions than it naturally would prefer. And so with that, we decided to move more deeply into one of these design strategies, namely that of aqueous reaction conditions. And so we what better way to look at aqueous reaction conditions than thinking about electrochemistry in a PEM cell? So here, I've demonstrated what this cell might look like on the right. We have methane going to methanol and proton-electron pairs. And then on the other side, those proton-electron pairs finding oxygen and forming water. The nice thing about this reaction is that we could turn methane into our valuable chemical, methanol, while at the same time getting 0.6 volts of electricity out of the process. So we have the possibility to pull electricity and make methanol. Unfortunately, there's our old friend, methane going to CO2 is a competing oxidation reaction that occurs at a lower potential of 0.17 volts versus RHE. And actually, the interesting thing is that this reaction has not been studied a whole lot, or it's not very well understood in the current experimental literature. But it would still be very valuable to have a system where you could convert methane to CO2 at room temperature and get electricity out of that system. And so for that reason, we moved to studying this more tractable system here. So when we look at the literature, we see there hasn't been that much work, but the work that has been done is largely on platinum-based catalysts. And so for this reason, Mike Boyd in the Jaramillo group synthesized some high surface area platinum electrocatalysts, and that's what we're going to be studying in this work. So here I'm showing the free energy diagram that we calculated for methane oxidation on platinum-211, and shown at several different potentials. All of the dashed lines we expect to be electrochemical steps, and so we haven't calculated barriers or kinetics for these steps. If you were at the talk earlier today, you would know that a large part of a PhD can be given to calculating these electrochemical barriers, so we're avoiding them here. But we do believe that two of the steps in the process that are important steps are thermal in nature. The first step, which is methane activation, methane bond cleavage, and then the second step, it's been shown previously in the literature that CO oxidation proceeds through CO-OH coupling on the surface. So when we look at the experiment, Mike has run some cyclic voltammetry data, And we see that even where we would expect CO2 production to be thermodynamically favorable, to the right of this blue line, we don't see any difference between flowing methane and flowing argon in the system. So no difference between it and our control. But actually, I just showed before that the methane activation barrier we calculate is just south of 1 eV. So it's actually a pretty high barrier. And this corresponds to, at most, microamps per centimeter squared. So this is actually not that unexpected. So instead, to see something, what we do is, or what Mike does, is a potentiodynamic control experiment where the potential is held at a constant potential for some period of time, and allowing methane to be activated and surface species to build up. And then the potential is moved to more oxidative potentials, and we do a positive sweep where we oxidize whatever surface species were built up on the surface. If we do this, so we're now holding at about 0.4 volts. If we do this, now we do see a significant difference between the methane and the argon in the form of this oxidation peak at about 0.8. And if we look back at our free energy diagram, we expect that this species being oxidized is likely CO, as that is the most stable intermediate that we had calculated on the surface for the relevant potentials. Some other things that we can do are change exactly what potential we decide to hold at. And so here the potential is changed from 0.3 volts all the way up to 0.6 volts. And that's, so looking here, you can see exactly where that is in terms of the CV on platinum. If we integrate the charge under the oxidation peak here relative to the argon baseline, then what we see is this sort of interesting maximum in the stripping charge here as a function of adsorption potential. At these low potentials, so about 0.25 up to 0.4 volts or so, where we see lower Q stripping features, we expect that that might just be due to hydrogen adsorption to the surface, competing hydrogen adsorption. And you can see here that the feature for the HUPD region is well within that sort of area. But we don't really know what's going on at the higher potentials, where we would still expect to be in the capacitive regime and not have any other competing species on the surface. So we want to ask why this charge goes through a maximum. So what we've done is to look at chronoamperometry experiments where we measure the current as a function of time at 0.4 volts, the maximum, and 0.6 volts, where it drops off. What you can see, just at a first glance, is that the absolute magnitudes of the currents seem to be lower at 0.4 volts than at 0.6 volts. So this is maybe suggestive that we have faster oxidation going on at these higher potentials, and we're decreasing the steady state coverage of CO. And so we can integrate the peak under here, and we can take the ratio of this this chronoamperometry charge divided by the stripping charge and plot these as a function of time. And again, what we see is that QCA over Q stripping for 0.4 volts is much, much smaller, 2 orders of magnitude smaller, or 1 order of magnitude smaller than the same thing at 0.6 volts. So this is really indicative of faster oxidation occurring of surface intermediates at these higher potentials. We can do a kinetic model to verify this hypothesis. We have only 3 important parameters here, and 2 of them agree very well with the experimental literature. 1 of them is generally not agreed upon. And what we find is that indeed, as we move from 0.4 volts to 0.6 volts, we see a drop off in the coverage of CO star on the surface. And this is in line with what is seen experimentally. We also see current densities that are on a similar order to what is seen experimentally, namely that at 0.4 volts we have current densities that are a little smaller than 0.6, and even the magnitudes of those are fairly similar. Given that this OH binding energy is not agreed upon in the literature, we decided to do a sensitivity analysis. In particular, a recent paper out of Mark Coper's group has suggested that OH adsorption actually is occurring at a very low potential of 0.27 volts, whereas normally these oxidation peaks at higher potentials are attributed to OH binding. So we ran our model at this suggested potential for OH binding of 0.27, the one we calculate 0.54, and the more traditionally agreed upon value of about 0.9 or so. And you can see the differences in the models here. Again, keeping in mind the experimental current densities, we think it seems unlikely that OH binds at such low potentials because the current density drops off pretty significantly, several orders of magnitude lower than what we predict with the original model. But we can see that increasing the OH binding to 0.9 electron volts doesn't significantly change our conclusions. It just widens the peak of this sort of great volcano. And finally, we can extend this to other transition metals and try to get an idea of why exactly it is that platinum has been so successful or has been really the most studied catalyst in the literature and the only one to really do this reaction well. So we have these three parameters I mentioned that influence the rate, but it turns out that the methane activation energy on transition metals scales with the CO binding energy. So we have a linear relationship here, and we can reduce these three parameters to 2. Now with only our CO binding versus our OH binding, we can plot two things. First, we can plot the log of the maximum rate that we would expect. So this is influenced by how good the catalyst is at activating methane. If it's very good at activating methane, then you would have a very high maximum rate. So you'd be down here. Also, though, we need to know what's the minimum potential required to get that methane activation rate, because we don't want it to be too high. So here in this plot, we'd like the minimum potential to be low, so that's red, and we would not like it to be high, shown in blue. What we find is that out of all of the metals studied, platinum seems to be sitting in one of the most favorable regions, namely that it has one of the weakest OH bindings, but also one of the strongest CO bindings. So we're in this sort of red region here where we have high methane activation rates, even though we have to go to relatively high potentials compared to some of the others to get that maximum rate.